Okay, so if you remember yesterday, we kind of finished a bit early because I say I don't want to start this and then, I'm not finished. Okay, because this is definitely, I think, going to be new for you guys. But yesterday, basically what we did is I think we did, a couple of examples, one for translation and one for rotation. We found the equation of motion. And basically, the idea was to show that no matter how was the system, you always ended up with the same type of differential equation at the end, okay, of the same form, all right? So today, and the way we derived the equation of motion was by just using the Newton's equation, summation of forces equal to ma, or summation of moments equals to I alpha, no? Okay, so there's another way to do that, all right? And that is known as energy methods. So let's see the colors. All right, here we go. So let's write over here. Energy methods to obtain equations of okay, so generally they give the name of this, the most popular name is Lagrange equation, but try to simplify it, but I'm also going to give you the Lagrange equation, okay, because generally the most widely used. Okay, so let's say the derivation is done in 1D for the sake of simplicity, but is valid for any dimension. Again, it's not important that you understand the derivation. What's important is that at the end, you know how to use the equation, okay? But basically, the main two equation is that what is the equation that we use to do a derivation? I mean, it's not that it's completely new, okay? Energy methods are based on the Newton's law, basically. But basically, this is Newton's second law that you are familiar with. And maybe just only you might remember from, I think, calculus 3, it said that if the force field is conservative, you can rewrite it under the form of a potential function V, okay? And generally in mathematics doesn't matter if it's positive or negative. Here we're going to put that is a negative, okay? Where V over here, this is just here, okay, this is conservative field. Where V is actually called potential. And maybe that's, I don't know if you did it, maybe you did that in dynamics. That's what actually they call the potential energy, because the potential energy is a conservative force, whatever, no? Okay? All right, so for 1D, let's see what will be the dimension. So if we use the equation summation of forces equals to ma, and F equal to minus alpha V, gradient of V, this will give us what? I can combine these ones, say minus the gradient of V, so the summation of forces will be the minus the gradient of V will be equal to ma. So now I'm going to move really into 1D. So this will mean that minus dv dx equal to m second derivative of x dt squared. Maybe here I went a bit too fast. Do you know what the gradient is, this one, what this is equal to, Charlie? I mean, if you want to put it here, this very quick is just partial xi plus partial yj plus partial z. Okay, no? All right. But if I do just 1D, I just keep it in x, no? Okay, for simplicity. So now this is the only trick that is needed over here. So I can write this as minus dv dx, and you're gonna probably recognize the other one. I can rewrite this term over here as m d dt of what? Of 1/2 d dx dot of x dot square. Before we move to the next step, x dot really means what? What is x dot? Yeah, but physically, what is it? The velocity, no? So what should be 1/2 velocity square? And if you put m, you could put the constant inside, no? So what should be 1/2 mv squared? That sounds like kinetic energy, no? So you see potential energy. We talk about a potential, can be potential energy. Now we see this kind of form of kinetic energy. Okay, so let's just go and check this part over here. All right, so I want to say check this part over here. So check, let's say d dt of 1/2 d dx dot of x dot square. So this should be equal to what? D dt of what? So the 1/2, we don't touch it. Now we take the derivative with respect to x dot, no? Okay, so it should be equal to what? 2 x dot. Okay, then I mean 2x dot, no? If you want, that's it. I forgot the, okay, yeah, that's fine. This is correct. So you can see, you can cancel this one with this one. And this at the end should be equal to what? X double dot, which is the same thing as that we had over here, no? At this step. What happened is I didn't put it on this term. I was just thinking about the same. But now when I substitute here, I'm going to rewrite that, okay? Yeah, I was thinking about the same thing. Okay, so now I can just say here. Therefore, maybe I can write this way. We're going to have what? I'm going to rewrite this equation here. I have minus dv dx, 1d. I can write this as being equal to d dt. Since m is a constant, I can put it anywhere I want. I can write, so I can, let's say, write this form, 1/2. That would be d dx dot of m x dot square. Okay, I can just rewrite now, minus dv dx equal d dt of d dx dot of 1/2 m okay, I'm going to put here the, yeah, so x dot square. But as we said, what is really this? What is the physical meaning of that term? Kinetic energy. So let's call it K. So basically at the end, I can just rewrite that minus dV dx. So V will be potential, will be equal to D dt d dx dot, or compared to the potentiality dk Okay, so basically, what is the stuff that we have just now derived? Is that we have said that doing summation of forces equals to MA, no? In the case of conservative forces, you can rewrite summation of force equals to MA on the which form? This one over here, no? So really, this is the same thing as doing summation of forces equals to MA. Correct? Okay? So this could be another way to derive the equation. So this is one way. This is the, I don't know how the name, but let's say energy method, okay? We could use that equation. But now I'm going to give you a different form. It's the same thing. All right, so you can decide which one to use. So I like more this one, but the other one is more like academic. So another form of the previous equation is known as the Lagrange equation and is derived as follows. Okay, but it's exactly the same thing. So basically, we have this term right here. We have the equation we start at minus m dv dx equals d dt of derivative of kinetic energy dx dot. Okay. So what he says is that adding one term on each side which derivative is 0, okay, should not change the equation, no? You agree? Okay, so what happens is that he says, okay, you know what? On this side, d dx, I'm going to put d dx. I'm going to say this is equal to k. So basically, it's adding the kinetic energy. But what is the derivative of the kinetic energy in function of x0? Because the kinetic energy is in function of x dot. Yes? No x, no? So this will be 0. Okay, so that's what he does. And then on the other side, he rewrites d dt will be equal to d dx dot. And basically following the same idea, here now is going to have k minus v. The derivative of the potential energy of V will be 0 because V is in function of what? Will be in function of x, and it's not in function of x dot. Okay? So that derivative will be 0. But, okay, I think it's complicated, okay? I think, personally, this form works fine, but, okay? but this one is the one most widely found in textbook. So then it says, so I'm defining K minus V as L, where L here is exactly the Lagrangians. We can rewrite the above equation as what? This sign over here is like the enter key on the computer. Okay, don't make up anything strange, okay? It's like, go next. So the above equation will become what? dl dx equals to d dt of dl dx dot. Okay, and we can leave it this way. Okay, and this is what is known as the Lagrange equation. But basically, you see that the only thing we have done is to add a constant, no? Okay, so we can do either one, okay? Okay, yes?
We're always defining alpha as k minus b.
What is alpha? Alpha, this is not alpha. This is I did like a weird L.
Yeah, that alpha.
Okay, yeah.
But that was always, it has to be defined. So like in the first chapter that we did, we also have to constantly write that L equals k minus b.
This is the first time I use this L. When did I use another L?
I just meant like related to where we said like the answer for the springs, like we always write the final answer and then we say where like Wn is equal to whatever the
I mean, this is okay. I don't understand the question, but this is energy. So the energy, the good thing about the energy is that you don't need to define really a coordinate system. It's global. When you say, and that's a good thing about potential energy. No, potential energy is a conservative force. But what do you say about the, for example, what is, okay, I don't know if that one is on direction, but of the answer that you're looking for, but what do they say the weight is path independent? Because it doesn't matter if you go from this height to this height on a straight line, or if you go all around, the change in potential energy is always going to be the same, no, between those 2 points. So it's path independent. So what I'm saying is that when you use energies, you don't need to use a coordinate system like you do with summation of forces. In here, you don't see any vector, no?
right.
I don't know if that was your question, but
It answered it.
okay.
Eventually.
All right. Okay, so basically what we're going to do now as application is that we're going to solve the same problems that we did before, okay, like yesterday, but this time using the energy form. Okay, so if I remember properly, I think we did one before that, but let's look at the examples. I'm not going to put number because I don't remember. I don't bring the class notes from the previous day. But let's go try to solve. So determine the equation of motion for the below system. And that system will be the spring now hanging on, and here we're going to say that, let's say our origin of Charlie, the other day we say that we need to select an origin for the coordinate system, no? Okay. All right, so we have this system, or let's say this will be, since we use X, let's call this one instead of you call it X, I think would be easier, okay? Okay, so let's follow the procedure. We can use either one, but for either method, we need to define the kinetic energy. So let's find the kinetic energy. K of this system will be equal to what? So what is the kinetic energy equal? 1/2 mv squared. But we know that V will be equal to what? X dot squared, no? All right. Then the potential energy is really, that's from where the name comes, is because if the force is conservative, you can rewrite it under the form of a potential function. And they ended up calling that potential function potential energy. Okay, but maybe you know the expression. So here, what type of potential energies do we have on that system? Okay, so we have spring and the mass, no? So what was the expression for the kinetic energy of the spring? 1/2 kx squared, no? Okay, so as you move the spring down, if you want, the potential energy of the spring is going to increase, no? Okay, here, that's the stuff you need to decide a reference value for the potential energy. Now, if you move down a mass, does the mass increases or decreases the potential energy? You have an object. If it goes up or lower, is it increase or decrease? I mean, if it increases, if you move mgh, no?
Right.
If you reduce it, then it will be minus mg, and instead of h will be x, no? Okay, so that's it. We can use either form. So the first example we're going to do both. All right. So maybe let's give a name to this equation. Let's call this one here A, and maybe this one here B. All right. So let's say over here. Using equation A, let's just rewrite it, which is minus dv dx will be equal to d dt dk over dx dot. So this will give you what? Minus d dx. What was the expression we had for the potential energy? We had 1/2. Oops, what did I do? 1/2 kx squared minus mgx will be equals to d dt of 1/2 mx dot squared. Okay, so let's see. What is this going to give you? If you take the derivative of this with respect to x, what are you going to get? So let's not forget the minus here. You're going to get what?
X minus mg.
So kx minus mg. And this will be equal to what? Will be equal to 1/2 of what? And this will be 2 x double dot, no? Yeah. So in other words, this will give you So this will give you what? Negative kx plus mg equal to mx of a dot, which would be the same thing as mx double dot plus kx equal to mg, which will be the same as x double dot plus k over mx equal to g, which are on the notes, but this should be similar to what we obtained last time, no? I think last time I did a change of coordinate system, so we get a 0 on the side, but we can have got this equation as well, no? Okay. So maybe you can do this one. I mean, I don't think you need me because it's going to be almost identical using equation B. What is equation B? So let's see, is D of Lagrangian dx, did I forget the negative sign on that one? No. Equals d dt of d of the Lagrangian dx dot, where the Lagrangian is defined as being equal to the kinetic energy minus potential. So maybe let me save some time, okay? So L will be equal to what? Will be equal to 1/2 x dot square minus 1/2 kx square plus mgx, no? So maybe we can do it directly. If we take the derivative of this one with respect to x, what is this be equal to? So this one is in function of x dot, no? So this will be 0, no? What will be the derivative of the second term? We end up with minus kx, no? In function of x. I'm doing this term, saving some time. Plus mg. Now I'm going to this term. So let's first do this part of the term. What is the only term that is in function of this one here? X dot. It's this one over here, no? So this will give you, this will eliminate, this will be 1/2, 2 times 1/2 mx dot, okay? But then you have the d dt all outside, so it becomes double dot. Yes? Okay. I mean, I'm saving some time, so we end up here with mx double dot, which you see design and designs are the same now. So it should give you the same thing. So let's say this will give us what? Mx double dot plus kx equal mg, or let me just write it, or x double dot plus k over m x equal g. Okay, and I think I forgot to put this one. Maybe let's put it now because I think that's the whole idea. This is equivalent to x double dot plus omega n x equal to g. This is x double dot plus omega n x equal to g, where omega n is what? Square root of k over m, no? So again, I mean, I could make it equal to 0 by changing again the current system, but okay, we're not going to redo it, no? So the x and stuff.
Is that omega squared?
Is omega square over here, you're correct. It's omega square here.
So since the equations achieve the same thing, like we just need to choose one.
Yeah, I don't care which one you use. Yeah, it's fine. Okay. The other thing, personally, I use more this one, but in textbook you'll find more this one. Okay, that's the reason I do both. Okay, so let's do another example, which was the second example we did yesterday. So again, we be determine the equation of motion, the E or M, for the below system. So it would be page 1, 2, 3, 4. Okay, so the other problem we saw, I think, was this time the rotation one, just the bar that is spin. And it's rotating. Okay, so in this case, the idea I'm going to add, all right, is let's say that initially when your bar is on move, that's the origin of your potential energy, no? Okay, now you move it up, you let it go. What's going to happen if there is no friction? This is going to rotate forever, ever, and ever, no? Okay, can I remove this stuff? Yeah. Okay, and we call this point here O. This will be CG. So this is CG as well. Okay, so let's follow the same procedure that we did before. What will be the value for the kinetic energy? This one might be a little bit more difficult. Remember, before we have kinetic energy, you can have kinetic energy due to translation and kinetic energy due to rotation. So the kinetic energy for the expression for the kinetic energy due to translation is 1/2 mv squared. What is the expression for the kinetic energy due to rotation? So, okay, so it will still be 1/2, but the m, let's say on there, let's look at it at 1/2 mv squared. Okay? In rotation, that should be substituted by what? So 1/2, nothing can replace it. What's going to replace the mass for rotation? I, perfect. And what's going to replace the v? Omega. So angular linear velocity will be 1/2 omega squared. Okay, here I'm going to add one thing. This is rotated about which point? Oh, so make sure you add O, because otherwise the I by default generally is taken at which point? At the CG. So we need to move it from the CG to that, no? Which I think we did it the other day, no?
Yeah.
Okay. I think we said that the CG is ml squared over 12. Once you move it to the n of the bar, it becomes ml squared over 3. All right? Okay, so then what else we have? Okay, let's look at potential energy. So this time there is no spring. So the potential energy will be what? mgh, but what is h? There's no x over here. What is h? H should be what? H is the change of height. This one, no? Yeah? Let's say we call this angle theta, that the bar, the initial length L. So let's say this is L over 2 and L over 2, okay? So what would be the change in height? Would be, it's not going to be this whole over here. It's going to be just the change this one, no? So would be equal to what? So mg L over 2 if you want at this position, which is L over 2, no? Correct? So I put this one minus now the distance from here to here, no? Yes? So it would be what? mg L over 2 cosine theta. So this can simplify, as you can say that then potential energy will be equal to mg L over 2. I should jump another line. This is too crowded. 1 minus cosine theta. Actually, yeah. Okay, so I'm not going to do both this time. I'm just going to do one. So do you want to use equation A or B? Okay, so using equation A, which is minus dv dx equal to d. Oh, and I might have to ask you something because we might have to change something, but let's change it later. If we have to change it, let's not do it now. The exact. Okay, so this will give you what? So now this equation here becomes what? We don't have x, but we have theta, no? So I could write this equation as minus dv d theta equal to minus d dt dk d theta dot. And then maybe I need to do one more thing here that I forgot to do. This would be equal to what? Omega is d theta dt. Okay? So maybe in this case, let's do a little bit more detail here. Is equal to minus d theta. What would be v? We say would be equal to mg L over 2, 1 minus cosine theta. What did I put a minus here? There's no minus here, okay? Equals to d dt of d theta dot of 1/2 I sub 0 of this. Okay, so what are you going to get over here? So the first term, the derivative of 1 will be, with respect to theta, will be 0, no? This is the only one who's going to take the derivative, no? What is the derivative of cosine? Negative sign, so we have negative sign, so you have still have a negative value, so we have minus mg L over 2 sine theta, no? And what are we going to have on the right-hand side? This will be equal to what? 2 theta dot, no? So the 2 will cancel out. Now we take the derivative with respect to this one. So this will be I sub naught theta dot dot. So at the end, we're going to have plus mgl over 2 sine theta. Is that the equation we got last time, or do we have a minus sign here? Because sometimes it can be plus or minus. Just want to make sure we get exactly the same one. Do we have this one with a plus or minus?
Oh, plus last time.
With a plus? Okay, so we're good. Okay. Okay, so I think last time probably we said that I sub naught is ml squared over 3. Correct? So this will become what? L squared over 3 theta dot dot plus mg L over 2, and then I'm going to skip one term here. For small angles, what do we say? That sine theta could be equal to theta. So we go plus mg theta equal to 0. If we divide everything by ml squared over 3, we get theta dot dot plus what? 3g over 2l theta equal to 0. I know I'm crowding everything at the bottom. Or probably we wrote this one as theta dot dot plus omega, I guess, theta square theta equal to 0, where theta omega theta was equal to the square root of 3g over 2l. Is that what we got last time? I mean, last time was yesterday. It's not that far away. So basically, now you have 2 ways to derive the equation of motions. Okay? So it's true that for very complicated problems, this energy method is very convenient. Okay? All right. I mean, any program, like finite element programs, are based basically on this kind of stuff, on energy methods, okay? All right. Okay, so we have seen the translation, the rotation, but now I'm just going to do another example for torsion. Okay, so let me go here for a torsional system. I don't know if I want to do that. Let's not do this, okay? I think it might just confuse. I have plenty of classes to use, so. I think now we're going to go more to the. All right. So let me use maybe a different page. It looks good. All right, so. Solution to the general form equation of motion for single degree of freedom. So what is the general form of the equation? Is we say it's always going to be on the form x double dot plus, let's say, omega n x equal to 0. Or let's say, I mean, if you change the variable, it will be the same, but this is what we have been deriving so far, no? Okay?
Is it omega?
Yes, omega n squared and this one squared, correct. I keep forgetting that today. Okay, so this equation is for undamped, okay, so it doesn't matter. This is not damped. Okay, so the general solution for either of the above two equations is found by assuming an harmonic solution. So basically, I'm not trying to scare anyone with the term harmonic, but harmonic makes you think of what? That's why I use that term. What do you think about when I say harmonic? You're thinking about what? You don't know? Okay. Sine, cosine, waves, no, that kind of stuff. All right. So that's basically what we're doing. All right. So that's what we're going to do. So let's kind of follow the procedure. So step one is what? Assume harmonic solution. So you have multiple forms of the harmonic solution. Okay, so harmonic solution, let's say the form will be x of t. So I'm just going to solve the top one, okay? Will be equal to, I need a different form. Let's say I call this one c for a constant exponential function minus lambda t. And then we'll see what each one of these stuff is. But basically, you know that the exponential function can write under the form of sine and cosine, no? It's the same thing. Okay, so if we have this harmonic solution, so we have here, this could be just theta t will be equal to c e exponential of minus lambda t, okay? So if we have this, so we have x equal to c exponential minus lambda t. What will be x dot? X dot will be equal to what? Minus c lambda exponential of minus lambda t. No? Simple math. And x double dot will be equal to what? Minus c lambda squared exponential of minus lambda t. Okay, this is pretty simple. You're going to see it. I think this should be page 4 or 5. Yeah, negative. I keep for you. Thank you. Positive. That's what I want. Thank you for paying attention today instead of me. So now, what do you think is going to be step 2? Okay, why do we do this? What can we do now? We can go and plug it in or substitute, no? So substitute into equation of motion. So remember, I'm using this one. All right. So let me just rewrite the equation of motion, might be just easier. So it will be x double dot plus omega n squared x equal to 0. So this will give you what? What is x double dot? X double dot will be c lambda squared exponential of minus lambda t plus omega n squared times x, that will be c exponential of minus lambda t. Okay, here now I can factor out by c exponential minus lambda t, and what do I get over here? I get lambda squared plus omega n squared equal to 0. So this is not even a differential equation. This was a differential equation. Now this is the solution. This is just one equation, no? Okay. So when is this equation satisfied? So let's have over here the above equation is satisfied if and only if what happens? What can be the two solutions? C, okay, I can put it here because can the exponential be equal to 0? No. Yeah? So the only option I've put here is when what? C will be equal to 0, then you have 0 times a term will be 0, no? So I said when this is equal to 0, but really this means when C is equal to 0, okay? So this type of solution here is 0 equals 0. This is what is known as the trivial solution. Now, what can be the other case of this equal to 0? Well, correct. So lambda squared plus omega n squared equal to 0. Okay. So in that case, over here, this will imply what? That lambda squared equal to minus omega n squared, which will imply that lambda will be equal to what? Plus minus I omega sub n. You know, I is mathematical definition is what? Is the square root of minus 1. Okay, one thing here, I don't know if it's good that I said, but depending on the book again, here you can assume the solution. It doesn't matter if you take c exponential of minus lambda t, or if you take c exponential of positive lambda t. Okay, you can take either one, no? You can do anything you want here. You can take anything you want, but you just need to follow some steps. So anyway, now that we know this, what can we do? What was the assumed solution? Okay, so we have this. Substituting back into the assumed solution. What is the assumed solution? this one over here, no? This equation here, assumed solution was this one. So we can have what? X of t will be equal to what? C exponential of minus I omega sub mt. So let's call this one C1 plus C2 exponential of I omega nt. Okay. All right, so nowadays, since you have computers, it's not that important, but basically this could be the end of the problem. All right, this is what we did. This is the solution. Now, so this is a general form of the solution. Now, the constant C1 and C2 will depend on what? So remember, what I was trying to solve here is, let me use this page over here, since I didn't use it before. Remember, let's say we use the one of the spring over here. We have the K and the M, no? And this was X, correct? X of t. So X of t, now the solution of this system moving in and out, we know it's going to be of this form, no? Okay? If you look at it, what will be omega n? Omega n will be the K over N, no? Yes? So we know this. This is not the real natural frequency. No. So now, C1, C2 should depend on what? Do you think? So basically what's gonna change is what? The vibration frequency is not gonna change, but what might change? So we know it's gonna be this way, no? So it's always gonna be the natural frequency, but what might change is the amplitude, because if we pull this one initially, let's say just 1 inch, it's going to start vibrating between that inch back and forth. But if you pull it 2 inches, it's going to be moving between plus and minus 2 inches, no? Correct? So what do you think these two constants will be taken into consideration? It should be taken into consideration the change in amplitude, no? Okay? So really this, we could leave the solution under this form, but what we're going to do on the old times, you don't have computers, just rewrite this solution here into a more physically representable solution, okay? And hopefully we'll get to the amplitude. All right? But this could be the solution. Okay? So you see, the steps to solve the differential equation is pretty quick. Six. Okay, so next, comma, let's rewrite the general solution x of t equal to c exponential minus I omega and t plus c2 exponential of I omega and t under a different form for a better understanding. Okay, so in order to do that, we're going to be using Euler's relations, which are what? You might remember now, but basically it's E I omega, or x you could have said is equal to what? Cosine theta plus I sine theta, and exponential to minus I theta is equal to cos theta minus I sine theta. Okay, so then we have this expression here, which is x of t equal to c1 exponential minus I omega nt plus c2 exponential I omega nt. We can rewrite that equation as what? As c1 cosine omega nt, so this one is the negative first, minus I sine omega nt plus c2 cosine omega nt plus I sine omega nt. I mean, do you see it's a direct substitution, no? I mean, this is just algebra. It's not, you're not going to learn anything new. So here I'm going to jump so I don't make everything too crowded. So you can see over here that we're going to have what? We're going to have C1 plus C2 cosine omega nt plus I of C2 minus C1 sine omega nt. Or you can write this as x of t equal to a cosine omega nt plus b sine omega nt. Where a will be equal just to c1 plus c2, and b will be equal to I c2 minus c1. Okay, so basically that means that we're not done. Okay? The modular form of this solution you see at the end is, we say harmonic solution, the exponential becomes cosines and sine, no? It's the same thing, there's an assumption. But personally nowadays with computers, I think this solution is plenty, okay? But we're not done, okay, with this yet. All right, so try not to do too much math. Okay, I'm going to change the video. So, all right, so let's say in a general problem, that way, let's finish this part. The general solution is found either using x of t equal to c1 exponential minus I omega nt, plus C2 E I omega and T, or x of t equal to A cosine omega and T plus B sine omega and T. Where the constants of integration. So here will be C1, C2, or A and B. Will be determined from the initial conditions. Okay, so these are generally the ones you will use in order to solve the equations, all right, to solve the problem. Okay, so I'm going to do it here in order to save some time. I'm going to do a reverse proof. I think it's going to be a bit faster. Okay, so the previous two general solution can be rewritten after some algebraic manipulation as, oh, we have time maybe to do it. Okay, so as x of t equal to the amplitude of sine, sometimes you might find cosine, doesn't matter, omega and t minus phi. Okay, where the amplitude, I don't think I'm going to do the derivation, okay? I might give it as an assignment. So A and P is the amplitude. Yeah, I think this is amplitude of a motion, and that will be equal to the two constants A squared plus B squared square root, and phi will be known as the phase angle, will be equal to the negative of the invert tangent of A over B. So I could do the proof, but I think I'm going to skip it. I'd rather do a figure with the physical understanding. Okay, so let me take one of these pages. So maybe before I do this in good time. So if you remember, we have been saying that we could replace the motion around a circle, no, by a wave that does something like this. Okay, so the amplitude is easy to understand. In our case, the amplitude will be equal to the radius, no? How much is going up and down. What is the phase angle? What is the phase angle? I mean, just like is that this is a solution when we start from here, no? Okay, but what will happen if we decide to start, let's say, from here? Then the solution will not start right at this point, no? It mean probably the solution may start, let's say, at this point here, and then it will go up, and then it will go be like that, like the zero will be here, no? All right. So if the solution doesn't start exactly at zero, basically that change in angle is called the phase angle. Does that make sense? Okay. So that's basically what I'm going to do now in the figure on the piece of paper. All right. So basically, I want to do the same circle, but I don't know how good I'm going to do at making circles. So let's see if I call this x of t. Let's call this t. Okay, so I'm going to try to do a general one. So let's say we start at this point over here. So there is a phase angle. So it should be the phase angle. So then what would that mean? That instead of starting here, let's say we start here at this point, no? Yeah. And then now where we're going to go? We're going to go from here all the way to the top. We're going to go all the way down to the bottom, all the way to the top, all the way to the bottom, all the way to the top, and so on, so on, so on. Okay, so we know this will be the amplitude will be the radius, where this would be here the positive amplitude. This one will be over here the negative amplitude. Okay, I think we kind of mentioned this a bit the other day, is that we said the time to go from, so I mean, it doesn't matter which, so the time is going to take to this point to go through one full cycle, no? Okay, if you remember, let's say we start from here, you go up, up, down, down, and up, no? So basically, if you start from this point to this point, this will be one cycle. Or if you go from this point to this point, will be once around all the circle, no? But here's just for the figure, I'm just going to do it here. So this could be over here. One cycle, no? So it should be here one cycle. Okay, so I don't know if we write that the other day, but let's say we're gonna have one cycle. So it goes once around the circle. So it goes 2 pi. This is to go once around the circle. How long is that going to take? We see what's going to take. T was the period, no? Correct? But now this depends on the natural frequency, no? Or how fast this is going. Okay, or here we could say that the natural frequency omega n will be equal to 2 pi over tau. And I think from the last time we also said that what will be the frequency. And I think, what do we say? That the frequency will be equal to what? I think we did that the other day, no? Will be equal to what? Look at the notes from yesterday. Or the first day, no, from before yesterday. So the frequency will be good. What are the frequency for the period? Okay, the period will be in time, no? Okay, so the frequency we say will be 1 over time, which is hertz, which will be 1 over tau, no? Okay, so so that we could say that omega n is also equal to what? 2 pi f, no? The frequency. Okay? Okay, so let me put, I know we did that there, but let's put here tau. This will also be tau, which is the period. So this is the amount of time it will take for the point to go through one cycle, no? Is the period or one cycle, whatever it is. All right, so I think today I'm going to finish a bit early again because I don't want to start something that I'm not going to finish, okay? I'm going to do one example, but so I don't see you until Monday, no? Okay, so I'm not going to add anything to the assignment on the first one, but imagine I might give you one on Monday, all right, about more about this stuff, about the equations of motion and so on. Okay, to find the equation of motion and to solve it. Okay.